Yeah, not even half. So take a deep breath, right? So, okay. Okay, so today, before continuing as usual, do you have questions, comments from the last classes? Stuff that you went back to your back home or to the hotel, was in the shower and had a brilliant idea. Oh, why didn't I think about it? Yeah, anything like that? Okay. Okay. So let's begin today's class, right? So I want to start talking. I want to start by talking about structured models. So what do I mean by structured models? It means that so far we have been dealing with compartmental models. What is a compartmental model? It's a model that takes the population, in this case the human population, but would be also animals and so on, and divides this population into compartments that are compartments relative to the status of the disease. So if you are susceptible to the disease, if you are infected and infecting with the disease, if you are recovered, immune to the disease, and so on and so on. Okay? Okay, but now this structure means something else. It means that not only I have these compartments relating to the disease, but you also have a structure in the sense that different individuals in this population will have a different behavior or a different response to the disease and so on, right? To the infection, according to their category. Okay, so I think I think one example that is really simple to understand, because it's kind of the stuff that we live with, right? So it's age, right? So if you think about age, right? So you think, well, population is divided. You can divide the population by age, right? So each individual has a different age, and I can do this like the whole age structure, right? So this pyramid, right? Yeah, you know this the demographic pyramid. Yeah, yeah. Everybody has this in their heads, or should I maybe find some plots in the Wikipedia here? I don't know. Yeah, you have this image in your head, right? So the age structure of the population is just that demographic pyramid and so on. Okay, you can have this stuff, and then you can think, okay, well, different individuals in the population with different ages can have different responses to disease. In which sense, right? So in one sense is, well, they can have different outcomes. So some diseases are much more dangerous for older people. Some diseases can be much more dangerous to younger children or to not so young children. Some diseases are more common among certain ages. For instance, diseases related to I don't know, work-related situations and so on are more common for people of working ages, so mostly between 18 and 60 or something like that, right? So this is so they're more exposed, right? So this is easy to understand, right? Yeah, yeah. But there's also something else here that is, well, also not only the response to contact to the disease, the response is different once you are infected, but you can also have a different structure in terms of infection of contacts between individuals themselves. Yeah, why? Because of course, if you are a child, right? Okay, you go to school. Yeah, right? You go to school, and in school, what happens? You are constantly in contact with dozens of other children. Yeah? So if you think in terms of contact rates, okay, the usual beta, okay, is it true that a given child will have a random chance of encountering people of any age? Like, because this on-touch rate that we had seen so far was assuming a well-mixed population. It means that, what it means well-mixed? All individuals have the same chance of encountering any other individual, yeah? Okay, but if we divide the population by age, is this true now? You can answer the question. The answer is obvious, right? Yeah? It's no, the answer. Yeah? Okay. So why? Because of course a child has a much higher chance of encountering other children. Yeah? Of being in contact, for instance, for, I don't know, airborne diseases or contact diseases and so on. It's much easier to transmit, if a child gets a disease, it's much easier to transmit to a lot of other children than to adults on average. Okay? Of course, children also have contacts with adults, but at a much smaller frequency. Yeah? They have contacts with, I don't know, their teachers, their parents, but not a lot of adults. But they do have contacts with a lot of children, right? So this means that our contact now is not only dependent on average of the whole population. It's going to depend on the age of the individuals, the age of each class of individual, of each age category. Yeah? Yeah? So how do we deal with this in our models? Yeah? So this is our first topic here. So our first look at this is age structure, right? So I'll try to then do what? I'll try to build an SAIFR model, but it's structured by age, yeah? Okay? Okay, so there's one part of this that is the part of the outcome, okay? I think this is the easiest part. Maybe we do this later, okay? But I think I'll go first for the hardest part. The hardest part is when you change the infection rates, okay? When you change the contact rates, okay? So let's do just this for now, right? So what do we do, right? So I had an S, an I, and an R before. Now I'll have many values for S, right? So I have young children, susceptible, older children, susceptible, young adults, older people, and so on. Each of them will have a different value, different number of susceptibles. Each of them will have a different number of infectious. Each compartment, you see, each age, I'll have to break each compartment, S, I, and R, into a number of compartments that is the number of age beings. Yeah? Okay? Okay, so for people that are more mathematically oriented, you're already thinking, well, but age is a continuous variable, right? Yeah? Or no, this is just my mind that thinks this kind of funny stuff. I don't know. So, okay, age is continuous. You can build a model with continuous age structure. Yeah? But then your susceptible will be a function of time and of age. And then this is an equation that has two variables, two independent variables, time and age. And this leads us to partial differential equations, okay? I don't want to go there, okay? I don't want to go there. This kind of equation here it will be similar in spirit to this PGE, but it's simpler to solve, it's simpler to understand. Okay? It is similar, we just won't deal with the technicalities of PGEs, okay? Okay? But you could do that, okay? You could. Okay, so here, I think it's already a bit complicated, okay? Let's divide this into age beings then, okay? Just for simplicity here, I'll take age beings of size 20 years, okay? 20 years. Just so I don't have a lot of age beings, okay? So I go from 0 to 19, 20 to 39, 40 to 59, and 60 plus, right? So at some point you have to stop, right? So I have to say, well, 60 plus, or maybe I go to 79 and then 80 plus, something like that, okay? Yeah? So I divided this population into these age structures, into these age classes, age beings, okay? But now I will look at, and this I would do in the board, yes. You look at, for instance, the equations for the first age being, okay? That is children from up to 19. Yeah, I don't know if this is children up to 19. Yeah, for my age, I can talk like that. I don't know. Juveniles, I don't know. Yeah. Okay. Well, at least none of you are as young as that, right? So I'm safe. Okay, good. Okay. No, no children. Okay. So I have this, right? So this is the equation for children, okay, for the first age class, right? And it should have essentially the same structure as before. I will have a minus here. It's proportional to the population of children, yes? But what goes in here, right? Now I have to say, well, I will divide this by total population. Yes? Or no? This is already, yeah, let me keep it like that, okay? Let me keep it like that. So, and here, what do I have to include? I have to include the chance of encountering infectious individual from each of the other classes. Okay, so I can have children being infected by other children, right? So this would be some beta times infectious children plus some other beta being infected by individuals, by adults. And now I have to call this by something, right? So I call this 0 infecting 0. I call this 0 being infected by 1. And now, and so on, right? So plus beta 0, 2, I2. Plus beta 0, 3, I3. And so on. Yeah? Okay? Yes or no? Does that make sense, people? Right? So this is essentially the same model as before, but now I'm saying, okay, each age being will have a different contact rate with children. Okay? Yes? Yeah, so this is a good question, right? So this is a very good question because when we built this model here, right, the SAIFR model, okay, we came here and said, okay, this is beta Si over n, right? And what is this n here? It's the chance of having an infectious individual in each contact, or so let me rephrase this. Is this equation here? Is it this? So each infectious has a number beta of contacts, each one with a chance S over n of finding a susceptible, or it like this. So each susceptible has a number of contacts, each of these contacts with a chance I over n of finding finding an infectious individual. Right? They are mathematically they're the same here. Yeah? Right? Do you agree with that? It doesn't matter. Yeah? It doesn't matter. But now, here, should I do this? Right? So each infectious individual of each age being will encounter susceptible children with this frequency here? Yes? Or should susceptible individuals encounter infectious individuals of other classes proportional to each of their populations? You see? These two models are different. Yeah? In this SAIFR model here, they are the same model. When I break up into classes, there are different models. You see? Yeah. And 0 is the population, the total population of children. So this S0 plus I0, yeah, it means that what I wrote over there is just wrong. Yeah? Yeah, don't trust these notebooks, okay? The people that wrote this, sometimes that it's not so right, yeah. Sorry? Well, yeah, sure. So this is the point, right? So you can do this in different ways, but then your beta should be interpreted differently. Yeah. And this is a trick question, people. After years working with this, sometimes I show, well, what is the exact interpretation of this? This is not so simple. Sorry? Let's start using the mic, right? So, over here.
So if n is constant, you can divide it everything by n and work with density.
The total n is
Actually,
constant,
it doesn't
but
matter.
n0 has some value, and 1 has a different value, and 2 is a different value because the size of the age beings are different. There are different numbers of children and adults and older people. So they're not constant. Like not all n's are constant, right?
Okay, but you can divide it by n and work with density. So I, S, and R will be densities instead of numbers, you know. Because all the time you are dividing by n. So you can do that in the beginning.
Yeah, you could, yeah. But then you are implicitly saying that your equation, if you say, well, shouldn't go like this. This should actually be already, I would define small s as big S over the population of that class, and then when I write it like this is something, that's what you're saying, right? So this is minus S, small si, multiplied by beta 0, 1, I0 plus beta 0, 1, small I 1, and so on, right? Something like this, yeah? Yeah, but when you do this, right? You see, this is, I divide by n0 on both sides to get this, and when you write this, you are implicitly assuming this shape here that assumes this guy here. Yeah? So, okay, you say, well, it's not natural, you know, it's a choice, you see? There are different choices, okay? There are different choices. So you just have to be careful. What exactly are you talking about, okay? So it's perfectly possible to write this model, but when you make this choice, you are making a choice for this interpretation here, and I would argue that it's much more common to use this shape here than this shape here, you see? So, yeah? Okay, so let's move on then. So this form here will lead us to keep these guys out here, okay? So this is number of infectious individuals themselves, and divide by the total population of each class down here, okay? If I use this interpretation here, okay? Not the other one, okay? So I'll go forward with this one, okay, if you don't mind. But it's not simple, okay? You can make either choice, and it's reasonable. I'm just going with what people usually do, it's not a rule, a law, or something like that, okay? Different models with slightly different interpretations, okay? Yes, are you comfortable with that, or? Yeah, sorry? No, it's n0. It's n0. Yeah, but there's no n0 here. Okay, so yeah. Yeah, because it's like this. Each infectious individuals of each age is going to have contacts with children, and what is the probability that these children are susceptible? Yeah, but you're looking at the probability of children being susceptible, not of, yeah? Mike, sorry.
That's why I said about the n. For me, that n is perfect on the board, on the slide, because you can meet people from Okay, you're talking about children, but these children are in a bigger population, right? That equation is just for a group. Was that the point? Just for a group?
You, well, of course you can. You can do something like this and already putting inside the beta here the information about the population numbers, yeah. But then this is slightly problematic because if you do this here, that is, you already include inside your matrix beta here, right? You already included the distribution of the population. It means that you cannot use the same beta 00, beta 01, and so on for different populations with different age structures. Yeah? Because you already included this into your betas, right? So you have to use a different beta for if you change different populations. Yeah? Oh, this is hard, right? So I know this is hard. Maybe let's try some example, perhaps. So, a toy example perhaps helps or not. So let's do something with only two age classes. Okay, 2 age classes. Yeah, you can say.
That equation is basically saying that S0 can be only affected within the children. That's not the case. That children can meet an adult, like you're saying, like
no,
I1,
of course.
I2.
Yeah, of course. All these guys here will also affect the other classes. Okay, so I have an equation for S1, where all of these guys will appear also in the equation for S1. And now there will be then an equation for S2, okay, where all these guys will appear also in the equation for S2. Yeah? The equation for S1, for instance, will be GS1 dt is going to be minus S1 over N1, in this case here, for instance, N1 multiplied by beta 1. You see, this is 0, 0, 0, 1, 0, 2, because this is infections from 0 to 0. And now it will be beta 1, 0, I0 plus beta 1, 1, I1 plus beta 1, 2, I2, and so on. Yeah? I don't know if that was a question.
It's fine, but that's like a conditional probability. You're saying that's not S0 divided by N0. It's not the probability to find a susceptible child. Actually, it is a probability to find a susceptible child given a child.
Yeah, exactly. But here, beta 0, for instance, beta 00 means that children contact other children with this rate. This beta 00 is the contact rate. There's probability of infection inside here and so on, but in terms of contact rate, this is the contact rate of children with children. Right? So it is what you said, this is the conditional probability given that I'm encountering children. What is the probability that that child is susceptible? It's exactly what you said. You're right. But it means that you have to divide it by the number of children, not total population. Yes?
S0 over N0 is the probability to meet a susceptible individual from an infected individual perspective, right?
Yeah.
Yeah,
well, I told you, it would be the other way around. Yeah, you could do this model as well. Yeah.
Yeah, but so then in this equation, the probability to meet one susceptible person, the probability to meet an infected individual is I0 over N, and then the probability to meet an infected individual from class 1 is I1 over N.
Yeah, exactly. So you could also build this model without this guy here and put dividing by N0, N1, and 2 over here. This is also possible, yeah? But then this is the ambiguity of the basic SAIFR model. It doesn't care about which of those options. But when you structure the model, it becomes, you have to resolve this ambiguity, yeah? And again, people, this is a model choice. It's not a rule that you have to always follow and so on, right? So it's a choice. So it's different possibilities are possible. You can write them, okay? Yes? Okay, so the thing is that there's a lot of stuff inside beta. Yeah, so beta it's usually like you have contact rate, right? Contact rate times probability of infection of the infected people the infected person actually infecting. And you can also have here, on the part of the susceptible person, the susceptibility of the person, okay? So, oops, susceptibility here, okay? So you have all this stuff here, okay? So I'm not so interested right now in looking at these guys here, but essentially looking at contact rate. So one way to think about this is looking at the unities of this beta here. What should be the units of beta in the SAIFR model? What are the units? You know what I mean by this, right? So, so this is population over time. This has population squared divided by population. So this is population. So beta has a dimension of 1 over time. Yeah? So beta, the dimension of beta is just 1 over time. Yeah? So there's no population there actually, yeah? So the contact rate is actually a pure rate, yeah? It's the rate with which each people encounters another person. Which person encounters another person, yeah? I think maybe this is what makes this stuff a little bit hard, right? So because there's no person, there's no people inside this unit here, right? So you have to interpret this as a pure rate, yeah? Yeah, well, I really should hope that Roberto would explain this before my class. Well, okay, I think he's better at conceptually attacking this, perhaps, I don't know. Well. I really wanted to just do some numerical simulations, man. Sorry. Yeah, well, so question for you, right? So question for you. It's clear that there's some room for doing slightly different model versions here, yeah? It's clear for everyone. Is this one here acceptable? Like, when I mean acceptable, it's not like, well, you're the professor, I believe you, and whatever, you know? It's like, well, I think this is a reasonable choice, and I would use this, and okay. Right? Because otherwise, it's kind of funny to just move on with something that you think is plainly wrong, right? So, yeah? Yes? Yeah. No. Yeah. Okay, sure. Yeah. S0 is N0, S1 is N1. That's what you're saying. The total population. Everyone is susceptible, yeah. Yeah. Yeah, now I have constraints for each age class, right? So I have that at 0. Yeah, I should have started with this, right? So for each age class, I have, and right now I'm looking at short time scales, right? So this is also important to note, that I'm not looking at aging yet, right? So for instance, if I'm looking at a dynamics of a disease inside the 1 year, I don't have to care so much about aging, about newborns, about deaths, and so on, okay? So this is a short time scale, so the structure, the pyramid doesn't change much from 1 year to the next, okay? So this is fixed, then the total population of children is fixed, the total population of adults, of younger adults, is also fixed, and so on, right? And then when you sum all of these guys here, right, you get the total M, yeah? Okay? So it's, the population is balanced. I'm not losing any people here, okay? So everyone goes somewhere, yeah? Yeah, but no, but this is the flux here. Yeah, not I'm not doing anything problematic here. This is not the issue. Yeah, the issue with using discrete age beams, right, that I told you about, is that if you want to include aging, now aging cannot be continuous here, right? So I have. If I, how would I include aging here? I would have to write in my equations, for instance, for S0, for instance, I would have to have an aging term here that would, so this is usually, I wrote an M for maturation, right? So of people leaving S0 and going to S1 because they are aging, right? So they are leaving this age class and going into this age class, right? And if you have an age being of size 20 years, right? So this is, you are taking random individuals from this class and going to this class. This is weird, right? Because usually only 19-year-olds can go to the next class, not, you cannot promote an individual from 1 year of age to 20, right? So, yeah, and when you do this in a PDE, then you follow this exactly, right? So individuals age continuously, okay? Of course, you can do this of OGEs if you use small age classes, right? So if you use, I don't know, one year by year and so on, then this works better, okay? Can you use the mic? I didn't get half of what you said, sorry.
What I was trying to say, since you are divided into subpopulations this way, and the total number of susceptible infected and in each subpopulation divided by N0 makes sense. But if you are doing, for example, I was thinking S0 plus S1 is equal the total population N, it would not be so reliable or something treatable.
Okay.
You're assuming a time scale.
Yeah.
Time scale from aging and demographics and so on must be longer than time scale. So the population at the age classes are covered.
Yeah. More questions? More concerns? Okay. So let's see how we solve this N-of model, right? So, and here is an interesting thing, right? So I'm going to do this with just a few age classes, just so that we can see the plots more clearly and look at the matrix and so on. But one thing that I was discussing with some groups yesterday, and maybe a little bit also at the end, at the presentation of the groups here, is that, okay, now I had an SIR model that was pretty simple. I only had 3 equations, right? SIR, actually only 2, right? Because the first I didn't even need the last one, okay? So only 3 equations, but maybe even 2. And this was pretty easy. And now, if I do 4 age classes, I'll have 3 times 4 equations. Yeah? I have 3 equations for each age class, so this becomes 12 equations, right? And if I just do the same stuff, and now, oh, no, but I want to do in age beings of size 10 years. Now I have, I don't know, 7, 8 age classes. With 8 age classes, I will have 24 equations. Yeah? If I do 5 by 5 years, I have 48 equations. Yeah? But is a model with age beings of size 20 or size 10 all that different? Are they much more complicated, much more complex? Right? So this is an interesting discussion. Actually, number of equations is not a good proxy for model complexity. Of course, a model with age structure is much more complex than a model without age structure. But the number of age beings doesn't change much the complexity of the model. Yeah? Okay, so this is, of course, you will need more data to parameterize it, but if you already have that data, and we will use an example here with contact matrices that were estimated from data. I won't go into much detail about this, but this data already comes in 5 by 5 age beings of size 5 years, right? So you don't have to worry so much about like subdividing like 10 by 10 or by 20 years or 5 years. So you already have this data at this scale of 5 years, okay? Okay, so let's go back to this model here. I will forget about this right now. Sorry. I won't talk about susceptibility changing by age for now. And now I want this to be what? I want this to be lambda I is 1 over ni. Yeah? Like this. Yeah? So I have each equation is, if you look at each of them, they are just the SIR model, okay? But inside of lambda, I have 1 over ni multiplied by beta ij. Yeah? This is exactly what is in the board, right? So, okay? Okay, and this, okay, this and B, this beta ij here, it means that this is the contact rate between every 2 age classes, okay? Okay, this forms a matrix, yeah? Beta ij, okay? So this is a matrix, and write this as a matrix. So this is called the contact matrix, okay? Contact matrix, and this is pretty important in general for structure models, the contact matrix. This is maybe the main new ingredient here, okay? So let's look at this example here. Let's try to solve this model. I think it's better to turn off the lights, right? Okay, so this part is exactly the same as before, just importing libraries. Here I took an example that is the population of São Paulo in 2021. So we start with an initial condition, and now my initial condition has to be written more carefully, because now you see here that I divided into 4 age beings, 0 to 20, 20 to 40, 40 to 60, and 60 plus, right? Okay, and now what is my x0, right? Remember that my x has to be a vector, okay? So this vector is structured in the following way. First, I have the values of s, okay? S0, S1, and S2, and S3, right? So the 4 values are susceptible. And what are these values initially? Well, I'm saying that all of them, they're the whole population, okay? Yeah, so this R here, it just puts all of these values together, okay? And I'm saying, okay, these 4 values here are the 4 values of initial number of susceptibles for each age class. And now I have 4 zeros here for infectious individuals and 4 zeros here for over individuals, right? So the whole population is susceptible initially, okay? Of course, I don't want this because otherwise I don't have any disease, okay? So I include a new individual here in the 5 is, I have 0, 1, 2, 3. 4 is the infectious 0, and 5 is infectious 1, right? So this means that one adult, one individual from 20 to 39 initially infected, okay? I introduced this guy here in the initial condition. Okay, so let me maybe break this until here, okay? And let me just run this here and print this initial condition here, okay? I use it to have a, yeah, okay. Okay, so you see, these 4 guys here are the susceptibles. These 4 guys here are the infectious individuals. And you see that they are all 0 except for the second age class here. And these 4 last guys here are the recovered, okay? So far so good? Yeah? Clear? Okay. Now, everything else follows the same approach as before. I have to give you the time, so I'm going from 0 to 108. And now this is the contact matrix, okay? So this, I won't go into detail here, but these essentially are values that we got from this paper here. And it's a whole discussion of how to measure this, right? So this is actually quantitative social sciences, right? So people go and do interviews and chat and count the statistics on how many interactions and then how many contacts people have with each other, with other individuals of each age class, and so on, okay? This is not easy to do because you also have to have a working definition of what is a contact, right? That is not so simple as well. So this is for airborne disease, right? So for respiratory diseases, okay, that transmission through the air, okay. But this is not yet your beta, right? Because this is a kind of a contact rate, okay? So this is contact rate of children with children. You see that by far this is the largest value in this matrix, okay? Because children with children have a lot more contacts than other ages, and then this is probability of infection of adults on children, of older adults on children, and older people on children, and then this is probability of adults, younger adults by children, young adults with young adults, and so on, okay? So, and you see that this doesn't even have to be symmetry, okay? This doesn't even have to be symmetry. Okay, and now besides the contact matrix, I also need a constant in front that tells me about the other stuff that I had left out, that is susceptibility and probability of infection per contact, okay? So this, I would just say, I just assume that this is a constant for all the possible contacts, okay? So I would just take, so my beta is actually, my beta is actually a constant that accounts for probability of infection at each contact, multiplied by this contact matrix, okay? Make sense? Okay, now I have sigma. Oh, I don't have sigma anymore because I just deleted it from my model, okay? So let me just get rid of sigma, okay? Easy like that. And I have gamma, right? So I am here assuming that gamma is more or less constant. Older people were over a little bit slower, okay? So, yeah, just to make something slightly different here, okay? Okay. You see that now, when I write my function here, okay, that is going to be my differentiation, if you just look at this line here, it looks like a simple SIR model, right? But the thing is, these guys here, beta and gamma, they are no longer numbers. They are now arrays. They're vectors. Yeah, this is a matrix, and this is a vector because it changes for each class also, okay, for each age. Okay, you see in my model here, I had gamma I. It may change from one age to the other, okay? Okay, so far so good. What do I have to do inside this model here? First, I get the total population, Okay, and now, now this is total population. Okay, because my model beforehand had total population, but this is not right. Okay, this is not right. So we need total population by age. Yeah. Okay. So. Okay, so how do you do that? So first, let's do something different. Let's take this x here. I want to do SIR, okay? So I will write these equations here as vector equations, okay? So this is the equation for each s, for each I, and so on. I would say, well, the GSGT with s as a vector is just the vector lambda multiplied term by the vector s, okay? So I would produce from s the SIR. How do I do this? So let's go back here. This is at 0, okay? So I will do this stuff here. This is split this vector here into 3 parts, okay? So if I do this, oops, where's the home here? Yeah. If I do this, now let's see what happens, right? So, oops, not x, right? So I need at 0. You see, now I have an array here with 3 parts. You see, I divided this guy with 12 elements here into 3 parts. The first 4 elements here that are S0, S1, S2, S3. Now the second one is the values of I, and the last one here is the values of S. Yes? Okay? And when I write this line in here, what this does, what does this do, right? So this line just says, okay, S will be the first one, I the second one, R the last one, right? So for instance, if I do this and then I print, I don't know, I, oops, once again, yeah. You see, I'm just getting the one in the middle, okay? So this is all I'm doing. I'm automatically splitting this into the 3 parts, okay? And now, what is going to be my model? It's going to be just the derivative of f is going to be minus s. This is a vector, and this will be a vector. And this multiplication here is multiplication element by element. Okay, so this is the derivative of s. The derivative of I is s times lambda minus gamma times I. Again, this is a vector that has 4 elements. This is another vector that has 4 elements. The multiplication just multiplies element-wise, element by element here, okay? And I get back a vector with the derivatives of I. And finally, the GRDT is just gamma times I. Again, these are vectors, okay? And the final, what I have to return back, okay? I have to return all of them put back together. How do I put them back together? I have this function R here that actually is the same I use it up here, right? So I just put them back together with this guy here. I put them in the order of the derivatives of S, of I, and of R here, okay? So it's pretty simple, actually, okay? What is missing still that I skipped? I have to calculate lambda. How do I calculate lambda? Lambda is the matrix product, okay? So this asterisk here, you have to remember that it's always element-wise product. If I want the matrix product, the math product, okay, with the stuff of summing over the elements in the lines and columns and so on, you need to use this function dot here, okay? So I want the dot product here, the matrix product of the matrix beta by the vector I to get this stuff here, this in the first line, beta 0, 0, I0 plus beta 0, 1, I1. This is the dot product, okay, the matrix product, okay? And at the end, and I have to multiply by n. What is n? Right now, it is the total population, but I don't want this. I want this to actually be the sum of what? The sum of each ageless. Yeah? So I want this to be a vector with n0, n1, n2, n3, n4, okay? So there are 2 different ways to do this. I could do it like this, okay? But I actually already have the total population here, okay? So that is actually this guy here, yeah? So I can just transform this into a parameter, or is this cheating too much? I don't know. Yeah, okay? Of course, here I probably need to update this because I summoned one individual here, right? So if I want to be perfectly honest here, I should also do this, right? So I have to do this also, right? So I have to subtract this one. In order for this to actually be the total population, I couldn't just sum a new individual here without taking it out of the susceptible population. Yeah? Okay? So I just put a new parameter here that is the total population, but not the total population summed, but the total population already divided by this guy here, okay? Yeah? Okay, so I just do this. And now when I divide it by n here, I'm not dividing by the total population. This n is a vector with population for each ageless. Okay? Before I was summing the whole thing, right? So before I was doing this. When I do this, I sum all values of x. So this is total population. Yeah? But I don't want to do this. I want to do age by age. Yeah?
Yeah, but isn't n a matrix?
Sorry?
Isn't n a matrix?
It is going to be a vector, not a matrix. This vector here, yeah? It's going to be this vector, yeah? With the individuals of each subpopulation.
Oh, okay.
Yeah? I could call something, yeah, it's really a good idea to, instead of calling this n, right? So let's call it by yeah, something like more informative. Yeah? So this makes, yeah? Makes life more, yeah? So, and so this now has another parameter here that is beta, gamma, and age structure that is going to be this variable here, the population over here, okay? So with this, and now I can delete this guy here, okay? Now with all of this instruction here, you see that in the end, my code is not too large still, right? So I split the initial, the x here, I calculate lambda, I write the same equations as before, and return this, okay? I would actually have put all of this together as we had yesterday, okay? Just, right? So, you see, and this code here should work, and now I will solve this calling this function, the initial condition, the times, and the list of parameters here in the same order as they appear here. You see that this exact same code works with any number of age beings. You see? What do I have to change? I have to change the initial condition. I have to change this population structure here that should have more age beings. And my contact matrix here should be an n by n, right? So the number of age beings by the number of age beings, right? So, yeah? Okay? Other than that, but the code itself is exactly the same. The part that solved the differential equation is exactly the same. Okay? Right, so I can solve this now. Okay, so I run this. And of course, I introduce some error at some point here. Why there's yeah, okay, so this is weird. Okay, and I have the solution now. Just before we plot this, right? So what is the shape of this x here now, right? So I had times from 0 to 108 in point 1, so this is 1,800 time steps, right? By 12 columns. What are the 12 columns? The 12 values of, 4 values of susceptibles, 4 values of I, 4 values of R. Okay. Okay, and what do if I do this now, I just plot as before, well, this is a mess, right? Yeah? This is a whole mess here. Yeah? Why? Because I have 4 susceptibles with different values, 4 infectious, 4 over. This is really hard to understand. Yeah? So what do we do instead? Okay? So we split again, right? So, but now I have to be careful with this splitting because beforehand I had only 12 elements here to split in 3, right? Now I have 1,800 by 12 to split. Okay? So I want to split not the whole stuff, but only the columns, okay? So this is split, and this means split by the columns, okay? Split the columns, not the lines, okay? So this split here means that S now has 4 elements, 4 columns, and still have 1,800 lines, okay? And then this has 4 columns, and this also has 4 columns, okay? And now I want also, it's hard to compare because you're usually interested not in total numbers, but in the prevalence by age, right? So it will divide each of those numbers by the population of that age class, okay? Yeah, so look at the small s here, okay? So I divide S, the total number of susceptibles at each age class by the population structure, okay? So this is a vector, this is another vector with 4 elements, and so on. I do this for S, for I, and for R. And now, instead of plotting all of them together, I'll do a subplot with only the susceptibles, only the infectious, and only the recovered, okay? And I'll have 4 lines in each. So this is, yeah, 180 was a little bit too much, right? So let me run again with less times just to make the plot a little nicer. So yeah. So now this 900 by 12. This plot is still a mess. Okay, but this plot now should be nice. Okay, so you see, susceptibles, they all start with everyone susceptible at 100%, and it goes to a number close to 0 here. Okay, and infectious, more or less the same, but you see that 0 is children, then adults, older adults, old people, and you see that older people tend to take a little longer, and younger people are getting the disease a little bit at a little faster rate here right at the beginning, right? So, but it's very subtle, yeah, very subtle, okay? Yeah, why should this, let me look up, take a zoom at this one here, right? So I want to look exactly between, I don't know, this is 10, between 5 and 15 perhaps, right? So just at this plot here, I'll do something to limit here the range from 5 to 15, okay? Here it goes. You see, now it's easier to see, right? That actually children are getting infected at a faster rate here, you see? Yeah, when you zoom in here in this A of just, I don't know, I thought of this in terms of days, right? So this should be in a single week, yeah? So they, on average, get sick a few days earlier, okay? Why is this? It's just because the contact rate between children is higher inside this matrix here, yeah? So these numbers here, they're higher than other numbers, and this contact between children is the highest number, okay? So this means that children will be infected faster, okay? Nice? Yeah? This is not as strong as it would be because this number is not like many times higher, okay? It's just a little bit higher than other numbers, okay? One thing that we can do is we can plot this contact matrix as well, right? With our p-color function that we had yesterday, okay? So this is, yeah, it's showing me 0, 5, but this is actually the first. This is 0 with 0, 0 with 1, with 2 and with 3, and then so on, right? So this is the on-touch rate of all classes infecting children, all classes infecting, you see, adults infecting adults, older people infecting adults over here, and so on, okay? So you see more or less that this has more or less a diagonal structure between adults. This is pretty much more homogeneous, right? Because people from 20 to 60 interact more homogeneously than older people and children, okay? And then you have this kind of stuff here, okay? So this is, yeah, nice. Well, this was nice or not so nice? Let's see. So interesting, I don't know. More complicated than yesterday, right? So a lot more, right? Okay, okay, good. So can I move on to some other stuff? So let's talk a little bit about spatial structure. Yeah. So this is another one that is going to be a little a little difficult. Okay. So the idea is similar. Okay. I will once again look at different subpopulations, right? So so we'll have an SIR model again, but now I have different locations, right? So you can think of this in terms of cities, you can think of this in terms of, I don't know, neighborhoods, or in terms of regions inside, I don't know, a state or something like that, okay? But it's always difficult in practice to do this, right? Because when you do this kind of division, it's always a little bit arbitrary, right? Because the data you have is usually by administrative regions, right? So you have data by city. You don't have data by urban area, okay? We are in São Paulo, right? São Paulo has a lot of urban area outside of São Paulo, yeah? Right? So a lot of cities close to São Paulo that are essentially parts of the city, yeah? So it's, when you look at the data for São Paulo separately from the data of the neighboring cities, okay, you are kind of having a partial vision of this, right? So, but this is a very hard problem to deal with, okay? So because essentially all data we have is by administrative regions, okay? We don't have data for aggregation, urban aggregations and so on, right? So it's hard. Okay. But then let's not worry about this right away, okay? And let's think of just a very abstract case where you have cities that are very well separated and so on, right? And then we have, okay, we'll build an SIR model for each city, okay? And this will look just as the previous equation, right? So I have SI, but now the index I will be the index of the city. So I have city 1, city 2, city 3, city 4, and so on, and each one will have an SIR, okay? Yeah, this is easy, okay? And if there were no human movement between cities, this would be, each of them will be a completely separated model, okay? I have the model for city 1, another model for city 2, and these are two SIRs with only changing, I don't know, total population or some other parameter, but other than that those are completely different models, okay? Completely, you can run them separately, okay? But now, of course, what we are interested in is, why do I build a model like this, okay? Because I want to talk about spread of disease between cities, yes? Okay. Now, how do I do this, right? So it's more or less similar with what we had before, right? I'm going to say, well, I don't know, suppose I am having an epidemic. I have two cities, okay? And I have an epidemic in one of the cities, yes? So I have infectious individuals in this city. And I say, okay, people from this city travel to the other city, and people from the other city travel to this city, okay? So they're exchanging individuals, right? One thing that you have to be careful here is that usually this, in rare cases, do you actually have migration, right? At least at short time scales, and I'm really focusing here on short time scales. In short time scales, you don't have a lot of people moving from one place to the other, you see? You have two cities, their populations should remain constant across a short time scale, yeah? It's not like they're packing, they're moving, establishing a new home in the other city. No, they're just traveling to do something else, something there, and they go and come back, yeah? Okay? So you can think of this like a pendular movement, right? So they go and come back, okay? So they're traveling between cities, and what actually establishes a contact between cities is suppose that city 1 is having an epidemic, and you are looking at individuals at city 2. Either you have to have an infectious individual from city 1 going to city 2 and infecting people there, or you have to have people from city 2 going to city 1, getting infected there, and then going back to city 2. So city 2, yes? Okay, one of these situations, okay? If people go to city 1, get infected there, but don't come back, then you don't have the disease arriving at city 2 back, okay? Yeah? Make sense? Okay. So now we'll have something similar. We can say, well, now my contacts will be, I will still have this contact of individuals from this city inside this city, but I will also have contacts with people from other cities. Of course, here, the structure is pretty much clear because it's kind of obvious, right? If you are looking at cities that are actually different cities, right? Not close neighbors, right? Not cities that are actually one, right? So that is much more common for people from one city to interact with people in the same city, and contact with people from other cities is a lot less frequent. Okay, so I will have essentially the same stuff here, but the diagonal elements beta 0, 0 is going to be much larger than the contacts with the other cities. Yeah? And the same for the city 1. In city 1, that is going to be, I don't know, S1 here. On city 1, this guy, the contacts among individuals of the same city will be much larger than the contacts with individuals of other cities. Yeah? Okay, makes sense? Okay, so we build this model like this. So once again, we will have a lambda here, okay? And here, I will assume that gamma is the same disease, so people don't change that much among cities, right? So they should have the same over rate, yes? Yeah.
Maybe can we change gamma intercities for example, São Paulo has metro. São João del Rei don't have.
But does that change the recovery rate?
No gamma beta.
Ah, you might change beta. Yes, you would. Yeah, you would. Sure. You could have. This is a long-running discussion, I guess, in epidemiology. Are larger cities, contact rates in larger cities higher than in smaller cities or not, right? So because you have mass transit that in smaller cities you don't, but on the other hand, there are other factors in, it's a long-running discussion, right? But you could argue in that direction, yeah?
Let me just mention, that's the same discussion as in the first class. It's the same discussion as in the first class about the kind of incidents that we can have. If we have the standard incidents or the mass action incidents. The mass action incidents would be not divided by n, the equations, and the standard incidence makes the equation be only frequency dependent, or the fraction. The only important thing is the fraction of susceptibles infected and recovered with relation to the total population. So what is being assumed here is always standard incidence, so that you don't have this kind of effect that things are very different between cities.
Okay, so this, of course, now this stuff is pretty much the same, and now this is more or less obvious that I have to divide by an I here, right? Because now I'm looking at the SAIFR inside each city I, yeah? Okay? If I had this beta here being only the diagonal, okay, only beta 11, beta 22, beta 33, the contact inside each city being different from 0, this would reduce to the basic SAIFR model for each city, okay? So you have to divide it by an I here for by the population of each city, okay? So ds1 dt is minus lambda 1 s1, lambda 1 s1 minus lambda 1, and this guy here is 1 over n1 beta 1 1 I1, okay, for CT1. Yes? So this is much simpler, yeah? Okay, nice. And of course, what happens here now is that inside this beta here, I'll have a small chance of one infectious individual from some other city infecting people from this city, okay? So this is this beta ij, okay? Of course, this can happen, as I told you, in actually two different ways. It can happen by people from city J coming to city I, or people from city I going to city J and coming back, okay? But this is, so it's, Mike.
In J city, and it bumps with SI, with probability SI over NI in city I. Right?
Oh, yeah.
That's the other way around. And it's different from the first example.
Yeah.
That's why.
Yeah, exactly. It's a little bit different from the first one. Yeah. Okay. So now how do you solve this, right? So it's pretty much similar. So here I'm using a more just guessing some values here, okay, not any particular city, okay. So I'm looking at 3 cities here, not to be too large, okay. So one with 1 million individuals, 300,000, and 100,000 individuals. Now the initial conditions are going to be, once again, everyone susceptible. This is the POPs here, the populations of each city. Now zeros for I and zeros for R. Now I put some 10 individuals, infectious individuals, on the city, on the first city, right? The city with index 0, okay? And now I take it out of the susceptibles and put it inside the infectious, okay? Now I once again define the time range, define all the, and okay, now here, I have to build the on-touch matrix, okay? I will build this on-touch matrix. How do I do that? So I will say that there is a frequency of traveling, okay? There's a frequency of traveling. So let me go up to here and do this step by step, okay? So this is the first part, okay? Now let me break this stuff here, okay? So what is this doing here, right? So I'm going to say that my on-touch matrix is what? I'll say that if I have most of my on-touch, this is proportion, right? One, if I, so yeah, before doing this, right? So let me print something here. That is this guy here, this I. What is this I here? I is a diagonal matrix, okay? So if I print this, you see this is a diagonal matrix. If I had no on-touch between cities, I will have 100% one, proportion 1 of city 1 with city 1, city 2 with city 2, and city 3 with city 3, and 0 on-touch among between different cities, okay? Okay, but now I'm saying, okay, there's a frequency of travel between cities, okay? And so what do I do? Well, I have 2 other cities, okay? I'll subtract 2 times this frequency from the main diagonal and put it in all of the others here. So let me print this on-touch matrix over here, okay? After doing this calculation here. You see, so now I have, yeah, this is wrong, right? I shouldn't, because I summed this including in the diagonal, right? So, yeah, I told you, don't trust people that write these notebooks, okay? So, it should sum to 1, right, in each column and line, okay? So, yeah, so I should actually subtract 3 here, yeah? Okay, now it's better, right? Yeah, okay. Okay, so what I'm doing, I'm saying, okay, I spend 1 over 1,000 of my time in this city and 1 over 1,000 of my time in this other city, Yeah, so I'm assuming here a constant travel frequency between cities, right? So I'm assuming that each city has the same, the proportion of travelers is the same in all of the cities, okay? Just for simplicity, right? And this now is my contact matrix, but this is just the frequency of contacts, of relative frequency of contacts with people from the same city relative to people from other cities, right? This is not yet a contact rate, so I still have to multiply this by some B0 here, right? That accounts for contact rates, total number of contacts per time, and also probability of infection, susceptibility, and so on. So this is what this B0 here is accounting for, right? And then my beta at the end here is going to be exactly this matrix, but multiplied by a constant here, okay? But this now, if I had that the beta before was 0.3, it will be slightly below 0.3 inside each city, but has also some other contributions from the other cities, okay? Does that make sense? I think this example is actually easier than the previous one, right? So, yeah. So now I have to define also the overlay rate and as of for your comment, right? So if I want to have different betas for different cities, instead of multiplying all of them by the same contact rate, each city would have a different contact rate. So I have to multiply each line by a different constant, yeah? Okay, and now everything else is pretty much the same. Once again, I do the split tree here, okay? I split the populations, okay? I calculate the lambda. Yeah, this is bad, right? So I use it a global variable. I shouldn't be doing this, right? So, okay. Oh, yeah, over here. Okay. This stuff here just calculates beta times I divided by population of each city, and then this is actually the same code as before. You see? So, and now you solve the equations with the SIR spatial, initial condition, time, and parameters here. Okay, and now I will once again plot it by city. Okay, by city, not by. Yeah, I'm dividing. Why didn't I use the split tree here? I don't know, okay? I should probably have done this. No, here I'm plotting SIR for each city. Okay. So this is, well, this is 3, okay? So this takes columns 3 by 3, okay? So I take the first, and then the fourth, and then the 7th value. So this takes SI and R for city 1. This takes SIR for city 2, and this takes SIR for city 3, okay? And divides SIR by the population of city 1, population of city 2, and population of city 3, okay? This is why I didn't do the split, okay? Makes sense. And now I have this 3 dynamics here. Remember that I started with infectious individuals on city 1 here, on this first city. So it's you see that the growth here of the infection, of the epidemic here starts earlier, okay? And this should start a little bit later, okay? Because I started with this city here. Yes? Okay? Questions? So maybe let's do the other plots as well, right? So I don't know, it is interesting also. Let me use this plot over here, this plot here, okay? So maybe plot SIR, yeah, like this. I think this also makes a little bit of sense to also have this plot down here, okay? So I will split again like this, but now I divide by POPs. That is the population for the cities, and I guess this will work, hopefully, yeah? And now I have susceptible for each city, infectious for each city. Why is this so weird? This is very weird, right? Wow, sorry. Up here I had this X-ling here, sorry. Oh, no, oof, much better, right? Sorry. Okay. Infectious for each city, you see that in city 1, it arrives first. And it's funny that it actually arrives a little bit early in city 2 than in city 1. Funny. The only difference between cities 1 and 2 is different populations, right? Yeah. Okay. Yeah. I'm not sure if I expected this, actually. But it kind of makes sense because this is prevalence, and at the very beginning, sorry? Yeah, if you go back to the numbers, right? If you go back to the numbers, then if you didn't divide this, right? So if you, instead of doing this, you did this, right? So, yeah, oops. Yeah, still you have, yeah, but they're going together, and then it saturates weekly, more weekly for the city with less people. Yeah, so it makes sense. Yeah, they go together here at the beginning, but then it starts to saturate faster for the smaller city. Yeah, now it makes sense. Okay. Nice people. Yeah. Already with 3 cities, it's already interesting to interpret this kind of stuff, right? So I think the other plot is nicer, but yeah, okay. Questions, I want questions.
It's kind of the same, right? Instead of cities, beings of ages, cities, because you use NI both.
Can you speak closer to the mic?
If you change cities for being of ages, it's the same because you use NI in both. So that was the only difference. Now it's equal. It's the same.
Yeah, well, they're pretty similar. Yeah.
The only difference was the N. Now it's exactly the same, right?
Yeah. Yeah. Yeah, but the interpretation of beta is different. Yeah. It looks like the model.
No, the difference is that the scales are very different. So if you have like 1% in one class of age, it's in a different scale than a city with 10,000 individuals and 1 million individuals. The scales are very different. The model is the same.
Yeah. Of course, this is also because I chose short time scales, right? For longer time scales, the model for cities wouldn't change so much if the populations of the cities are not changing, right? But for age models, then you do have to take into account number of births, number of deaths, and the aging of the population, right? Because this also changes as in Roberto's classes, right? So what happens when you have an endemic disease in an aging population, right? Younger people, in general, are less immune because they didn't have as much time to get the disease yet, and then you have a distribution of prevalence with age, right? So, and this changes the behavior of stuff like that, okay? So in the spatial case, it doesn't change anything, yeah? So you don't have, you know, one city is, you know, like you don't have people moving through cities in the same way as they move through age beings, right? So it's actually different, but at very short time scales, they look the same. More questions?
Just to mention that in cities you could have time more easily time variation of the contact between cities.
Yeah, yeah, yeah. There's also true. There's also true.
Age structure longer time scaling.
Yeah, and actually, I chose a very idealized model here, but actually if you have a lot of cities and have a network of cities, and then the frequency of travel between cities would be different. Here I chose 3 cities with homogeneous travel frequency, right? But of course I would have cities that are closer together, or there's an end of law of gravitation for cities, right? So bigger cities tend to exchange individuals at a much larger range, at a much larger scale than smaller cities. So instead, for instance, São Paulo and Manaus have a very large rate of exchange of individuals, even though they are very far away, right? So because you have airports connecting them, like you have planes connecting, so connection via air travel is much more important than physical distance, right? And this kind of connection is linked also to, I don't know, historical, geographical, socioeconomic issues and so on, right? So, so this kind of natural, it is quantifiable in principle, and Marcelo does a lot of that, right? So work a lot with this kind of network structure of movements of people, okay? So he probably has something to tell about it at some point. I don't know.
What I was going to comment is that actually that's an important point. Then if you want not only to connect now to 3 cities and so on, in this idealized case, but yet you want to say I'm interested in the spread of a disease, and say in Brazil, and like COVID, for instance. So you start probably at a big city, São Paulo or Rio, importation, and then in your contact, your beta matrix that was around there, you can put the network structure of the connection between, for instance, airports or roads. Depends on how detailed you want to do the thing. So that's the way to introduce the network there. Okay, it will be in the betas in this case. Okay, so this is a bridge to how networks will appear here. So in this case, which is a simple case, it will be networks with connecting through airport with some weight. Okay, so São Paulo Rio has a lot of flights, but São Paulo, I don't know, a small city in Mato Grosso maybe has only 1 flight per week. Okay, so you have to put some weight. Okay, but then you need to know the network of airports and structure of these connections, and you can put it in a beta, and then you have a SIR model which includes a network structure.
More questions? I have left a few things out of this, right? So the first one that is actually more relevant to the age example, right? The age structure example is variation in outcomes. Okay, why did I left it out? Because the SIR model doesn't have any difference in outcomes. Okay, people always get over. There's no difference in an SIR model between mild cases, severe cases, and so on. Okay, so for this you would need to have a model that does account for this difference, right? I don't know if you have seen this already or not. As models with different outcomes. No. Okay, so maybe in 3 minutes we don't have time for that, right? So. Okay, but no. Maybe it's worth to talk about this real quick or not. It's up to you. If you have a lot of hunger, it's our time already. Yeah, so maybe another time. Okay, so. Okay, but the other, just to finish, the other thing that we left out is that this example here is a little bit, with the cities, right? It's a little bit funny because it reaches a situation where sometimes it's important to go back to the basics of the formulation of these models and think, okay, why do we use OGEs? Okay, we use OGEs because, well, this is a process of transmission. You have large populations, a large number of people, so it's okay to just approximate the number of people by a continuous variable, right? And you just look at the averages, okay? But when you have the process of new arrivals, okay, when you do OGE models, if I get 0.01 individual arriving in a city, in my model, this already starts an epidemic. In real life, you need a full person to arrive at a place, okay? So, yeah, okay? So this is the kind of situation where sometimes, depending on what you're looking at, the approximation, because what happens is not, what is happening here in the other two cities, okay? It's not that a lot of people from here, infectious individuals, arrived here, okay? It's just that a very tiny amount of infectious individuals arrived here, and then it ignited the epidemic process in the other two cities, okay? So, and this timing of arrival is the main point, okay? This timing of arrival, right? So, in these OGE models, you always have tiny fractions already starting the epidemic in the other cities, okay? The point is, sometimes you don't want to do this. If you want to really account for the time it takes for disease to arrive in other cities in a more rigorous way, right? Your continuous models don't work so well, okay? So this is when you go for stochastic models, okay? And do you have to completely abandon your OGEs? No. You can still use the OGEs once the disease is established in a single city. Then you can use your OGE to see how the epidemic curve happens in that city. But the process of arriving, of one individual arriving, right? This is essentially happening with integer numbers, not with any 0.1 individual. Yeah, okay? So one way to deal with this sometimes is to build kind of hybrid models, and of models that couple a stochastic process, that is the arrival of one of the initial individual in a city, okay, in a city that doesn't have the disease yet, and the continuous model, the dynamic model with OGEs of the spread of the disease inside each city. Okay, so this is one possible approach that is kind of in the middle way of complexity. Okay, I don't want to go for a full stochastic model, but this exact part of the model is very, very sensitive if you really want to, compute, well, how long does it take for the disease to get to the other city and so on. Stochasticity matters in this situation, okay? So this is the kind of problem where if you want to go for stochastic stuff, yeah, this is it, okay? So at least from my perspective, okay? Okay, so I have talked too much already, so let's have lunch then, okay? So thank you.
So what's going to happen in this afternoon? Okay, so so you have your group work, the usual one, usual afternoon, but we don't have a session at 6 today, okay? So just work on. There will be a seminar at 2 by our invited person, Guillaume Letreux. And this will be, I think, more for the physics community of the institute. So not so much on our subject, but if people that have a background in physics, a little bit more advanced background in physics, if you want to just come to the seminar, that's fine, okay? So you will need the keys, so of your